In this video, we are going to discuss how to calculate angular momentum of a rotating object and apply the law of conservation of angular momentum. The figure shows a student holding a dumbbell in each hand with their arms initially stretched out. The student stands on a platform that is freely rotating about a frictionless axle. Each dumbbell has a mass of 2.50 kg and they are located 1 meter from the axis of rotation. Calculate the angular momentum Li of the system given that the initial angular speed omega I is 0.8 radian per second. The combined rotational inertia of the student and the rotating platform is 2 kg meters squared. So here in this question, we have a student who is rotating on a rotating platform and their combined moment of inertia, which I will write I for the platform and the student as IB equals 2.0 kg meters squared. And they are rotating with an initial angular speed omega I of 0.800 radian per second. The student is holding two dumbbells and each dumbbell has a mass MT, T for dumbbell, of 2.50 kilogram and they are located at a distance which I will write as R of 1 meter from the axis of rotation. We need to find what is the initial angular momentum Li of the system. Angular momentum L is given as I times omega. So if I want to find the initial angular momentum, I have to multiply moment of inertia of the system with its initial angular velocity. Moment of inertia of the system is the sum of moment of inertia of the student with the platform and moment of inertia of the two dumbbells. Since the two dumbbells are identical and at a same distance from the axis of rotation, we can just add their moment of inertia and write this as 2 times id into omega I. Now we know all of these quantities here except for moment of inertia of the dumbbell. We can treat the dumbbell as a point mass and we know moment of inertia of a point mass is mr squared. So we can rewrite this expression as Li to be equal to Ip plus 2 times mass of the dumbbell into r squared into omega I. So Li becomes equal to, let's substitute the values. Ip is 2 plus 2 times mass of the dumbbell is 2.50. Their distance from the axis of rotation is 1 squared. Omega initial is 0.8. And when you solve this, you get the initial angular momentum to be equal to 5.6 kg meters squared per second. Now let's discuss part B of the question. In part B, a physics professor stands at the center of a frictionless turntable and holds a dumbbell in each hand with their arms outstretched. While rotating, the professor pulls the dumbbell inward such that they are closer to the axis of rotation. What happens to rotational inertia, angular momentum, and angular speed of the system? Now, the general rule for moment of inertia I is cmr squared. That means this moment of inertia I is directly proportional to the square of the distance from the axis of rotation. Larger the distance from the axis of rotation for the same mass, greater will be the moment of inertia. So in the initial position when the arms are outstretched, the moment of inertia is the greatest. And when you bring the arms close together, the value of R decreases. And if R decreases, moment of inertia will also decrease. So when the professor brings the dumbbell inward, its rotational inertia has to decrease. Then part 2 of the question is asking us what happens to angular momentum. Now according to the law of conservation of angular momentum, if there is no external torque acting on the system, angular momentum before must be equal to angular momentum after. So the total angular momentum before when the arms were outstretched must be equal to angular momentum when the arms were brought inward. So there is no change in the angular momentum of the system. In part 3, we have to discuss what happens to the angular speed of the system. Now we know that angular momentum is related to angular speed as L equals I times omega. Now for a system with no external torque acting on it, the angular momentum remains constant. Now when the professor brings the dumbbell close towards him, the value of moment of inertia decreases. But the angular momentum of the system remains the same. If you want to keep the angular momentum same, you need to compensate for the decrease in moment of inertia. So to compensate for the decrease in I, the value of omega increases. So when the professor pulls the dumbbell inside, his angular speed increases in order to keep the angular momentum constant. So here we can say that the angular speed increases. So when an object is spinning with their arms outstretched, when they bring their arm close together, their rotational inertia decreases, which increases their angular speed to keep the angular momentum constant. Now let's discuss part C of the question. A physics professor stands at the center of a frictionless turntable with arms outstretched and a 5 kilogram dumbbell in each hand. He is set rotating about the vertical axis, making one revolution in 2 seconds. Find his final angular velocity if he pulls the dumbbells in towards his stomach. His moment of inertia is 3 kg meter squared with arms outstretched and 2.2 kg meter squared with his hands at his stomach. The dumbbell are 1 meter from the axis initially and 0.2 meter at the end. So here in this question you have a physics professor rotating on a turntable with dumbbell in each of his hand. Mass of the dumbbell, which we will write as mt, is 5 kilogram. He is making one revolution in 2 seconds. That means this is the time period t, which is 2 seconds. Then moment of inertia of the professor when his hand is outstretched, which we will write as ip initial, ip for the professor, which is 3 kg meter squared. And initially when his hands are outstretched, the distance of each dumbbell from the axis of rotation, we will call it r initial, is 1 meter. When he brings his hand close to his stomach, his moment of inertia, which we write as ip final, is 2.2 kg meter squared. And now the position of dumbbell from the axis of rotation, which we call as r final, is 0.20 meter. We need to find his final angular velocity. So we need to find what is omega final. Now we know from the law of conservation of angular momentum, initial angular momentum Li must be equal to final angular momentum. Initial angular momentum we can write as product of initial rotational inertia times the initial angular velocity, and final angular momentum we can write as final rotational inertia times the final angular velocity. We need to find what is omega f, so we can rearrange the term and write omega f to be equal to I initial omega initial over I final. Let me call this equation 1. We will find each of this term in this equation and then substitute here to get the value of omega final. Let's start with omega initial. Omega initial can be written as 2 pi f, where f is the frequency, and frequency and time period are related as f equals 1 over t. So let's substitute that here. We get omega to be equal to 2 pi over t. So we get omega initial equals 2 pi over time period t is 2 seconds. That gives you the value as pi radian per second. Then we find what is initial rotational inertia, I initial. Now rotational inertia or initial moment of inertia has to be the sum of moment of inertia of the professor and the dumbbell. So we write this as IP initial plus moment of inertia of the dumbbell. Now since there are two identical dumbbell which are equidistant from the axis of rotation, we have to add moment of inertia for both. Now there are two dumbbells, so we need to add moment of inertia for both. And since these dumbbells are identical, they have the same masses and they are at the same distance from the axis of rotation, so their moment of inertia will be equal. So I can just write their sum as 2 times the moment of inertia of one dumbbell. Then how do we calculate moment of inertia of the dumbbell? We can treat each dumbbell as a point mass, and we know moment of inertia of a point mass is mr squared, where m will be the mass of the dumbbell and r will be its initial position. So we can write I initial to be equal to Ip initial plus 2 times mass of dumbbell into R initial squared. Now let's substitute. I initial becomes equal to initial rotational inertia for professor is 3. 2 times mass of each dumbbell is 5. Its initial distance from the axis of rotation is 1 squared. That gives you the initial rotational inertia to be equal to 13 kg meter squared. Now we do the same thing to find the final rotational inertia. Final rotational inertia again will be rotational inertia of the professor when his arms are closer to his stomach, plus again 2 times It. This will be equal to IPF plus 2 times mass of each dumbbell times R final squared, because this is at the final position. Now substitute. IPF is 2.2 plus 2 times mass of dumbbell is 5. Their final position is 0.2 squared. That gives me I final to be equal to 2.6 kg meter squared. So once I found each of the values from equation 1, I will substitute here to calculate omega f. So we get omega final to be equal to I initial omega initial over I final. Now let's substitute. I initial is 13, omega initial is pi, I final is 2.6. That gives me the final angular velocity to be equal to 5 pi, or you can write this as 15.7 radian per second. So you notice when he brings his arms closer to his body, he rotates much faster. That is because the angular momentum must remain constant. And when he brings his arm closer to his body, the rotational inertia of the system decreases. And if the rotational inertia decreases, angular velocity has to increase to keep the angular momentum constant.